Thanks for joining all. We're just going to give it a couple more minutes before we get started here. Hello, everyone. Good morning, good afternoon, or good evening, depending on what time zone you're in today. And welcome to the 2021 CxEnergy virtual webinar series. And special thanks to Senseware for sponsoring this presentation. Before we get into things, I do have some general housekeeping notes to address. In order to receive a certificate of completion, you must be a registered attendee and use the personalized link that was sent to your email address to join the webinar, not any link that might have been shared with you. Once each live presentation concludes, you'll receive an email with your certificate within 24 hours. And please note that you don't need to use the CxEnergy app this year. Some of you returning may have remembered it from 2020. Additionally, and this is a note for ACG, EMA, and ABC members, if you are a certified CXA, EMP, or TBE, staff will be uploading your certificates of attendance to your respective member portals for you. This will be completed after the final CxEnergy virtual presentation at the end of April. All live webinars are being recorded, so if you happen to miss one, you'll be able to view it 1 week after the live event. And then during the session, we encourage you to submit questions at any time using the Q&A button. The chat function is where you can make general comments and chat with attendees. And if you happen to be experiencing any technical problems, please use the chat function to inform the panelists, and one of our technical experts will assist you. Today's webinar is the future of recommissioning, how to prepare your facility to be IAQ centric. And a few words on our speakers. Raj is currently president of a full service mechanical, electrical, commissioning, and plumbing consulting engineering firm located here in Washington, DC, with 9 offices specializing in institutional projects, energy modeling, data science, and high performance buildings. He's also on the ASHRAE Epidemic Task Force for schools. And Raj is joined today by Serene, the CEO and co-founder of Senseware. So without further ado, let's get into things, and I'll hand it off to Raj and Serene to kick us off today.
All right, thank you. And I am going to share my screen and begin. All right. Okay. All right, thank you. I will begin. Just some housekeeping items. Again, this is Raj Setty, myself, and then Serene with Senseware. You are getting the AIA credits. Lower this. This materials are copyrighted, but if you do want to share these or get access to them, let me know, and we'll make sure you get that. Today, we're going to talk about indoor air quality, the new paradigm that we're we're moving into where we have to start to look at air quality as one of the primary factors in indoor design and also commissioning. And then we'll talk a little bit about a case study that we're working on. So by the end, hopefully you'll understand what defines a functional performance test for indoor air quality, as well as what we need to start to look at on remembering that how these are all going to start working, and is it working? All right, let's see, next. All right, we'll go through, here's the table of contents, and let's just get started. A little bit about SETIs. We mainly do engineering. We do have a commissioning division, and we are moving heavily into data science and looking at all of the data that we're gathering across control systems and making design operational changes to bring the building back into energy savings, as well as now indoor air quality. Serene?
Yep. Hi, everyone. This is Serene, CEO, co-founder of Senseware. And our mission at the company is to help people gain a sense of security, that they're aware of what's happening in their physical environment. And we do that by connecting the different types of data sources and sensors that are around us that present information that our natural eyes don't get, from mechanical, electrical, environmental, or plumbing.
All right. Oops, sorry. So the main guidance out there, let me make sure this panel, is this panel in the way? I think so. Okay. The main guidance out there you're going to see in the marketplace is CDC, there is EPA, and both of those organizations come back to ASHRAE for the technical guidance. And with ASHRAE, we're continually improving and updating the guidance by sector, offices, residential, even polling stations and schools, and I'm on that committee. At the beginning of the pandemic, ASHRAE was very clear, saying that it was a reduced airborne exposure. It was an airborne infectious pathogen. So we have taken that position from the ASHRAE front to make sure all of the guidance was geared towards that. When all is said and done, we have three main tools as design engineers, and then as commissioning agents that you will need to monitor, which is ventilation, disinfection, and filtration. Those are our three main tools. And by altering those and modulating those, that is how we're going to slow and mitigate the virus transmission. Moving forward also, though, is we want to now start to shift the paradigm away from COVID as vaccines are put into place, and move into what is the best indoor air quality for our occupants. There's a lot of good benefits from higher cognitive function, as well as just moving the CO2 out and making sure that we have really good air systems in place. The next few slides, I'm going to just go into the education of what we are trying to do on indoor air quality, and then how the design will progress, and then how we move into commissioning. So a lot of what we look at is particulate, especially in the West Coast when we're looking at the fire season and how we filter the particulate, and what does that particulate mean when we start to sense inside. Generally speaking, you'll see some terminology on PM 2.5, PM 1.0, and PM 0.5, and that is going to be the particulate size on the micrometers, and that's what we're showing here. So viruses, especially the SARS virus, it's here in the 300 nanometer wavelength. It does not travel by itself. It attaches to particles. So when we talk about different pandemics, influenza, you want to start looking at the particle size. And it is really, it's easy to kill the SARS virus because it is what's called a enveloped virus. So it has a very weak outer shell. So part of some of the technologies when we go into like UVC, those will help to stop the replication and breaks them down. So as we start to talk about the education, make sure we understand the size of the virus and the size of the particles that we're trying to pick up. There is out there a Wells-Riley equation, and the Wells-Riley equation will model the virus transmission risks. You can go to SETI.com and download one that we've built, but when you're creating an OPR, when you're creating the basis of design, one of the things that people will ask you is, how can you model the risk? What is the percentage of my space where I will get infected if there is another person who is infected? So when you have a infected person, they generate what's called quanta. That's this Q. So as you breathe your quanta and your other occupants have longer time of exposure and you have lower air change rates, then over time, ultimately, your probability of infection goes very high. So if you have, and you can use the sniff test on this. If I'm outside in a classroom, I have an infected person and I'm 10 feet apart, my probability is very low. If I'm in a dorm room and I'm 24 hours, my probability of getting infected is very high. So same way, we can define that with the Wells-Riley equation. So make sure as you start to create these OPRs that you do create a concrete number based on the Wells-Riley equation of what you would like to see, and as you guide your owners. Same thing, we will, with ASHRAE, we are putting out guidance between 4 to 6 air changes. You'll also see the term CADR, clean air delivery rates. So where those come from is the studies here. It's asymptotic. As you start to increase your air change rates, always more is better, but you start to lose capacity, you start to lose effectiveness on that as far as the 10% and the probability of infection. So that's where we've kind of settled on this 6, roughly. We are talking about moving to a square foot of CFM number, but most systems don't have the ability to go beyond that 6. And typically we're around 2 to 4 in most standard designs. Humidity. So a lot of the studies in the past have been based on influenza, where we look at the relative humidity. And so between 40 and 60% infectivity plummets for influenza. Now, we do know that the SARS virus and influenza are both enveloped viruses, so they act reasonably similar. But moving into the future, if your clients need to have a space that has the lowest probability of infection, then we may be looking at putting in humidification systems to keep our humidity between this 40 to 50, 60% relative humidity. But there is a lot of studies right now showing below that 40%, your percent of infectivity drastically goes up. So maintaining your relative humidity, if the goal of your projects is to reduce airborne transmission, then you need to look at humidification. Next, filters. So MERV 13 filters is where, through the ASHRAE guidance, that we've provided the best filter sizes for capturing the virus. Going back to the size of the virus in that 300, in the 3 micrometers. So if you can look at the MERV 13 filters down here in this composite chart on the bottom left, we're going to pick up roughly 90% of the particles. So then as we add multiple passes, if we have 6 air changes an hour, so we could get up to 6 passes every 10 minutes, we're capturing the particles that are carrying that virus at that size. So it's an indirect correlation that if my mesh size on the MERV 13s is picking up all viral particles at that 300 nanometer size. So think about, as we have different pandemics in the future, or we have different goals that you want to capture particles of a certain size, it's all about that filter mesh size. And of course, the best, of course, is HEPA, which is used in most of the healthcare applications, but it's very difficult to retrofit air handlers with HEPA filters due to the pressure drop at this point. And I'll talk about some of the other calculations we did. Next, you're going to start to get different technologies that we've categorized into this disinfection category. UVC is the most common, that's been used for many, many years. Ultraviolet in the C bandwidth at 253.7 nanometers. That's naturally blocked by the ozone, so it is introduced into different air handlers at the coils or in upper UV to stop the replication of viruses. It doesn't kill it, but as someone is generating quanta, they're generating viral particles, the UVC systems can keep up with stopping the replication and that viral load. You're going to see a lot of different technologies on there as commissioning agents. It will be your job also to evaluate and vet some of these different technologies. Where ASHRAE is standing right now, you'll see bipolar ionization as a very large deployment across the industry. There are things to think about with that. It is a good technology as long as you have a reputable manufacturer, and you have to be careful about the ozone generation. So if you're looking at bipolar, it needs to comply with the Underwriter Labs UL 2998, and that has I believe it's less than a 5% ozone generation. You're going to see things like, where's the one? UVV and UVA. Just again, be careful about the wavelengths. Those can be generated from the excitement in certain lamps. The lower cost lamps will let the UVV and the UVA out of the lamp. The higher cost lamps, they absorb the UVV and UVA and allow the UVC out to cause the disinfection. We're seeing vaporized hydrogen peroxide being utilized when there's someone who does have an infection and they come in and they just basically want to, I don't want to use the word fumigate, but put in the vaporized hydrogen peroxide to kill all biologicals in that space. So start thinking about these beyond functional performance tests, but almost as a commissioning, recommissioning, or a validation that a space is clean. That might come into your purview later on if someone says, can you assure that the space no longer has any viral load in it? And these will be some of the technologies that you'll need to deploy. Now we're going to go a little bit, so you have some of the tools and that are being put out there, and you should understand some of the education piece of this. Now we'll go into the implementation. Any new project that we're involved in, we are putting in a tab. We need to know the real numbers, not off of the design values. At this point, based on ASHRAE guidance, all demand control ventilation systems are disabled. We would like to run everything in maximum fresh air mode, maximum ventilation mode. So if your local area is 400 parts per million on CO2, start resetting all of those to that. It is also commonplace to have varied occupancy, and you have to disable your CO2 systems right now and run at 100%. Also tab and figure out what your true ventilation rates are and your true return side of that, of your air handlers. And so that's your baseline. And from that, the engineers, the commissioning agents can make their decisions on what technologies to start to deploy. Another piece that we found through, and we'll go into the case study, is the distribution of the ventilated air has to be monitored. So looking at what we're seeing with all the sensors being deployed, you'll start seeing the CO2 levels staying high at the end of run, which should make some sense. And that might lead us in retrofitting or designs to put small return exhaust fans, just pulling the air out of the space and dumping it into the plenum. So when we do see a lot of the VAV plenum returns, we're not pulling that air back out. So when we put in the sensors, we're looking to see if we are getting good distribution of our ventilation, and are we able to move that clean air into the new, the occupied spaces. So getting a sense of what type of air distribution and the real numbers on that has to be done as well. Second, there is, I learned way too much about filters. There's a lot of different types of filter media, and the MERV rating is your main place to equalize all these, but understand what some of the washable filters are versus glass versus the frames, the bypasses. So we have entered a paradigm where your ventilation and your filters are your low-hanging fruits that have to be addressed if your clients are saying, I want the safest possible air flow. So start looking at your filters, look at the change rates, and then as filters are ordered, commissioning agents, engineers are probably going to get pulled into helping validate the filter type of order and the media. If you do have filters that don't fit, then block off the bypasses, make sure there's no bypass air. And it's really important that, especially some of the school systems, some of the office buildings that don't have a good filter protocol, make sure that those are put into place. We're going to kind of move into the case study here. So with our DC public schools, the main theme was equity. They wanted every school out of the 117 schools to get some of the attention. So budget was 24 million, which equated to about 200,000 per school. They decided to go by school, not by school capacity or square footage, just because the 200 wasn't a huge amount anyhow. So the main things we did were do the three things we talked about: ventilation, filtration, and disinfection. And I'm always going to kind of go into those. First step was just figure out where we were. So we did do that testing and balancing, and we added a deferred maintenance list. The deferred maintenance list, anything that had to do with air side, which wouldn't allow our air systems to work properly, became a critical item. Dampers weren't stroking. Any of the motors weren't working, VFDs weren't working. So we did capture all of these on a singular list. It is also useful for your clients and yourself to create these deferred maintenance lists as a shovel-ready project for future funding that is being put together right now on the federal level and a lot of the school districts. So figure out what you have, what type of air, and then where you are. Next, we did a quick motor calculation. So when engineers size motors, they'll do a static pressure calculation, pick a motor on, or pick a fan with a fan curve and figure out where that is. We often put 10 to 20% factor of safety, and then we'll pick our motor. And so here's the first example on RTU1. We had a MERV 6 in there. Then we looked at, do we have the horsepower to shift onto that? So in many cases, we ended up bumping it up to MERV 13 without seeing any degradation in the motor capacity. Now, we have to always apply common sense. And so what we did was change all the filters. Finally, we just made the decision, change them all to MERV 13. If you start to see some degradation in the airflow, which is what you're going to see, then go back to the previous filter size. But future projects that we'll start to encounter is upsizing the motors and the fans if needed without actually changing all of the, without changing the air handlers. So it's very difficult to upgrade to MERV 13 on some of these unitary systems. In fact, it's impossible. So, but what could we get to? Could we get to a MERV 8? Could we get to a MERV 9? So those are things that we did calculate. Next, we looked at the entire school. This is an important piece that you'll have to look at when you start to figure out how you're going to create your OPR basis of design. So we created a total air change rate for the school. In this one, call it 80,000. We looked at all the air handling systems and we came up with roughly a 3.8 air change rate. From here, we created the projects to give us the clean air delivery rate. Currently, ASHRAE guidance, we're looking for between at least 4 to 6. And so we're trying to now come up with the different projects that will bump us up into that higher range. Sometimes it's going to be, could we increase fresh air? Could we run it longer? All of these were done. Most of the time, we ended up coming up with the portable air cleaners, and we deployed one per each classroom, 300 CFM to get us up to that 6. When you're running your functional performance tests for air change rates, these are things you'll need to look at, as well as treat the building as a contiguous entity. So when I run commissioning exercises, there's very few functional performance tests that look at the entire building and all of the HVAC systems running in unison. Too many FPTs are always about each different piece of equipment. But energy, and now here we are looking at the whole building. So what does this mean? It means that your gym units and your assembly units, which are your fresh air engines, may run 24/7 to drive more fresh air and overpressurize that into the building. If you look at this example, we have almost 5,000 CFM of fresh air for this building, but it's at the assembly. So we are propping open doors if they are worried about it and running the multi-purpose assembly space, driving that air into the rest of the building. It is clean air because it's fresh air at that point. The system has the capacity, so it is conditioned as well, and that air is at neutral at 70 degrees. So these are things that you'll have to make some adjustments as you're trying to target the 6 air changes between 4 and 6. Some sample sequence of operations that we deployed. We did put in sensors to see if the motors were getting overloaded. You'll have to adjust the sequence based on if you have a constant volume versus variable on that. You can set your freak drives to avoid any overheating or overloading of the motors. But on the constant, we did have some monitoring on there. This is mainly during the filters. Flushing the air handlers. Right now, our guidance is run all the air handlers 2 hours after occupancy. So that can be done prior to occupancy at 4 in the morning or after cleaning staff at 8. So those are sequences that need to be adjusted. Humidity overrides as well, making sure that if we weren't able to keep control because we're bringing in too much fresh air, then this is in the winter side because we don't want to drive the humidity down too low because that does propagate infectivity. It's mainly during the winter. Another place, of course, you have to disable your demand control ventilation, stop your heat wheels. All of this is all in the ASHRAE guidance, so I won't go into all that. A couple other ones we've seen out there. There isn't good verification it's working, but there are a couple air handler clients that are running their heating coils wide open, driving 180-degree water through them, but not running the fans. And that allows your entire casing and coils to heat up. It is a pseudo way to disinfect. The viruses will die if the temperature reaches over 140 in those air handling casing. So that is, again, a sanitation mode that I've seen deployed. On the air change rates, you will have to calculate them not just systems or building wide, but also in individual spaces. Again, we are targeting that 4 to 6 equivalent air changes or CADRs, clean air delivery rates. Think about sound also, and we do not want the noise levels, especially in classrooms, to go over 30 to 40. So you're going to see some very low quality air cleaners that will have not a lot of CFM, and they will be too noisy. So functional performance tests, sound has to be one of the criteria, keep it under that 40 dB. And now the main question is it working? And this is where Serene will tell you a little bit about that.
Yes, thanks, Raj. We, as you guys have also seen, that there are so much that's being deployed as measures to make healthier building, cleaner air. Raj touched on some that we did with this project, specifically at the schools. And there's always this question at the end. We put all of these great measures to handle the disinfection, filtration, ventilation. How do we know that's working? And that's where sensor data becomes really vital piece of the entire solution. When we talk about indoor air quality sensors, there are a few things to keep in mind. First, what are the different air quality measures that we need to sense and look at, and then the frequency. So when we are looking at the first question about what are the sensors to deploy, the best answer is to look at what are the measures that are being deployed and make sure that the sensor set that you're deploying is tying to those measures, so then you can answer the question whether or not these measures are working. And buildings are dynamic. We deploy a lot of measures that are static in nature. We change how much air we get, the filtration units and whatnot, but the usage of the building is dynamic. So it's really important that you get real-time monitoring around the clock across these measures, so that if things are not working, you all know how to improve. So as a standard, set of sensors that are highly recommended to be deployed is particulate matter sensors. Raj mentioned particles and how they contribute to transmission of potential harmful viruses and whatnot. So looking at particle matter and monitoring that is really important to add to the mix. Also, PM sensors are helpful to determine the effectiveness of the filtration strategies, because that's a big thing that's being improved in spaces. Carbon dioxide is another very important sensor to keep monitoring and data to monitor. CO2 levels can tell you two things: whether the air is diluted properly to continuously keep healthy air environment, also a proxy of how many people in the space and if that needs to be adjusted to create healthier space. We have VOC, which is volatile organic compound. This is measuring things that are emitted from cleaning products, but from furniture, paints, things like that. So especially with increased cleaning and in a lot of spaces, schools specifically, that's really important to keep an eye on that metric. But also this contaminant, the VOC, could be also used in figuring out whether ventilation performance is good or not. The other two I want to touch on, because of the new measures around UV and bipolar ionization that Raj pointed to, is to look at ozone levels, just to make sure that the products that are being deployed for UV or MPBI are not generating by something bad for us, like ozone. So that's another sensor to consider. And then ion sensors that also measure the effectiveness of ionization, if that's a measure that's being deployed. And there are other sensors that are out there. The one thing to keep in mind is also the location of the building. The conditions outside may determine other things, to other sensors to deploy. So for example, I talked to a school in south of Florida, and they were following ASHRAE's recommendation to bring more outside air. And that, because it's south of Florida, it's humid, and that created a humidity issue and a mold issue there. So for that particular region, it's really important to add humidity sensors so that you can balance between the recommendation to clean healthy air and also the actual conditions of where the building are. Other sensors like NO2, SO2, and things like that are for heavily polluted area, could be also used. Really important is to know that not all indoor air quality monitors are created equal. Again, if we're trying to look at whether or not these investment in measures to keep healthy air are working or not, it's really important to make sure that the sensor accuracy meets what we're trying to measure. For example, with the PM, if you're deploying or installing MERV 13, you may want a PM sensor that is really accurate, that could go down to 0.3 micron to know if that particular measure, the filters are working as they should. So you really have to make sure that you look at these things. IAQ sensors are rapidly evolving, just like Moore's law. Every 18 months, something new comes to the market, especially now with this global impact. So it's important to make sure and ask the question, when was this particular sensor manufactured, and make sure you use the right ones. Next. And this is just to give you a flavor of how the sensors come in different sizes and shapes. If you look at the CO2 sensor, for example, in the past, in the in the sensor world, the recent past, we used to use sensors that use light levels to get CO2 levels, and now the new generation is looking at vibration and sound levels, which is really interesting. So there are different options out there. Choosing the right ones is really, really important. So we can go to next.
So this is what the actual dashboard looks like with our Senseware platform. So we deployed approximately 10 sensors per school, call it about 10 sensors per 100,000 square feet, and we're monitoring all of these levels from temperature, humidity, CO2, VOC, PM 2.5. We collect roughly 2 billion discrete pieces of data per day. From that, we are now creating the action plan. So when we see PM 2.5 above the critical thresholds, that's going to be when we make the decision to change the filters in that HVAC zone versus differential pressure. And we can do both, but right now we want to keep the highest quality air in the space. When CO2 goes up, it's going to naturally go above. Here's what we're showing, some critical monitoring. When CO2 goes above our threshold, this dashed red line or this yellow line, what we're looking for is the decay rate. And as it decays within 90 minutes to 120 minutes, then we know our ventilation systems are working properly. But CO2 sensors are giving us the direct correlation that our ventilation systems are actually ventilating throughout the building, not just at the air handler. The PM is telling us that our filters are actually filtering. The most interesting thing that has come out of this is the VOC sensors. So when the VOC spikes, and that's the example I have on the screen, and each line here represents a sensor. We have 10 sensors represented here. I know it's a little crowded, but what these spikes are now indicating is that the room has actually been sanitized and cleaned, and the ventilation systems continually diluted, and we start to decay. So now we can not just say to constituents, that your room has been sanitized, but the data points are showing to what level and that it actually was done. One of the main things that we want to make sure in this new paradigm of air quality is to do no harm. So just by dumping bleach directly onto desks and over sanitizing will cause more harm than good. So that's what these sensors are allowing us to make sure that we stay within these bounds. We don't want to be walking into these classrooms and they smell like a hospital that's just been sanitized or formaldehyde. So that's what we're starting to now look at, the aldehydes, the zines that are all being generated by these different cleaning products. And the paradigm of air quality is, what do you have there? Serene, you want to do this one?
Sure. Yeah. So the other thing to also make sure to implement once you start to get the millions of data that Raj got is to make sure that you're acting at the right time and not just responding to every spike that's out there. So there are different things to look at as you are starting to look at sensor data. First is you want to make sure that you set the thresholds based on guidelines that are out there at what are the healthy levels are and what are not. And Raj can talk more about that. But also you want to look at the trends over time. So you can baseline for this particular location. This is the CO2 levels that are there. This is also remove anything that are known spikes. For example, you know that the cleaning is going to happen at these times. So you don't have to worry about getting adding that to the critical alerts that you get. So once you have all of that in place, you then can set the alarms. And you also want to add to that is how long of a period of time for this new critical reading has elapsed before you get alerted. Again, if we're looking at CO2, VOC, PM, and the level of decay. And if the level of decay is fast enough, we know that there isn't an issue. So we don't really have to worry about that specific incident. And so setting the time before you get a notification for each of the levels is really an important pairing to the thresholds that you set in the system.
So where does this all lead to? Where we're trying to now move to is to start to tie in these sensors into your control systems. So when you have the VOCs spike, if they don't start to dissipate on what we predicted, say 90 minutes, then that wants to automatically crank open your fresh air dampers and flush. So what are our tools? We only have a couple tools: more ventilation, longer run times. And those two things are going to be able to handle a lot of the indoor air quality problems that originate inside the building. If we're in the fire season, same thing in California, we want to be able to shut the outside air dampers if our PM levels start to increase inside. And so that's where we need to start to think about how we put these systems in place and then to automate it. And finally, energy consumption has to be taken into consideration during the unoccupied times. It is a pendulum between energy consumption and ventilation, indoor air quality. It's going to go back and forth. We're at the point that there is no tolerance for saving energy if it will compromise the indoor air quality and possibly spread infectious airborne diseases. So that's kind of where we have to have both systems into our control sequences and make sure that we handle them both. All right, so what have we learned as we start to think about commissioning and then retro commissioning? When you're generating your OPR, CFR, the terminology you want to start to talk about is, what is your risk assessment? What type of risk are you trying to design for? We can design for a hospital if that's what your client says, I want no possibility of transmission of any virus inside, then you're going to 100% fresh air system. You're going to treat it like a hospital. Now, that's going to be very costly. That's going to be very complicated to maintain, but you're going to start to see hybrids of that throughout your spaces. So for example, in a school, we may see 100% fresh air system at the nurses' suites moving forward. So we do know that it's a high probability that a sick child will go there, and we don't want any of those quanta to come back into our main HVAC system. So as you develop your space by space plan and your maintenance plans with your clients, then that's what you want to start to think about, the risk by space. Indoor air quality is in a new paradigm now. So think about water years ago where we started to put fluorine, then we chlorinated because that was the best for the occupants. Then in schools, we changed the entire menu. We took out vending machines because that was the best for the kids. So we have not done that level of retrofits for air quality, and that's what's going to start to move into the world. Simple ways to do this are on DC is we started to put a supervisory system-wide control system. So what this is now is we are looking at 117 and we're adding another 100 buildings to a single dashboard for the control. So we can push out a time change for operation to 7,000 HVAC units simultaneously. We can monitor system-wide if there is a event like a chlorine spill at the treatment plant, and lay out how that starts to look across the school portfolios in this dense urban environment. This will be something that will be useful for fire seasons, but this allows very fast changes to our two main levers: run the units longer and run more ventilation or less ventilation based on our system. Filter changes, those kind of things will occur normally and at the building level, but a supervisory control system is where we need to start to move, and it's extremely efficient when we need to make those real-time changes. To get there, it is complicated because there's so much data that is being pushed up into the cloud. So you need to have a way, these are kind of, there's a lot of different companies out there, so I'm trying to not be proprietary, but you have to have a mechanism to collect that data. You need to have a place to store that data, and there's different companies for all of this. How to describe that data. So a controls company XYZ, RTU is the same as the other company RTU. Then any cybersecurity, it should be read write. You could also go just read only. And then you move into the analytics. And this is what we're starting to push out there on that supervisory level, because the changes need to start to happen faster. And then AFDD, which is automated fault detection and diagnostics on the air quality, which is going to now be one of our primary driving forces when the kids are in class. That is what's going to drive our control sequences, our entire indoor air quality schemas and mindset. When the kids are in classes, priorities, highest air quality. Kids are out of classes, priorities, saving energy. So those are your two different competing interests that are coming. Typical reports that we're generating. So this will be a middle school. So we take all this data from Senseware, and we get this daily report that shows when things go above threshold. That's pretty high, 27,852 parts per billion for the VOCs. And then we're seeing, did our HVAC system work properly and did it go back into threshold? So here the answer is yes. We're always going to see these above thresholds, but did it go back to normal? Above, that, back down. So this is the same kind of classroom location. So then where do we go from a commissioning point or engineering point? It's why did it get so high? So we generally want to be well under 1,500. So something is happening that's generating a lot of poor air quality, and it took us 3 hours to get back to normal if we did have class during that time, because cleaning staff is coming in later. So that's where recommissioning and retro commissioning will be. Well, what happened? And that's where we're going to be as an industry put to task. And so the sensors are giving you this peek into the dynamic air. All right, and then we'll start looking at all the distribution patterns. PM, typically PM is going to generate from outside unless you have some experiments or science labs or things like that. But most of the particulate is pollen. It is going to be dominant from your ventilation system. So that is another thing that we are looking at now is, can we filter it, pick it up before it's being reintroduced? We need fresh air to get rid of all the CO2. So it's this balance that's occurring. There are some references that we can go into. And with that, I'd thank you for your time. Hopefully this starts to give you a new way to look at it. Here's our contact information, and we are happy to answer some questions.
Awesome. Thank you so much, Raj and Serene. Great presentation. We have a decent amount of questions, definitely people interested in this topic. So let's jump into it. First question, for COVID mitigation, if you needed to choose between increasing ACH or humidifying cold, dry outdoor air in a northern climate, which approach would be prioritized?
So if I was the design engineer, I would precondition and get your humidity levels as close to 50% or higher before occupancy. But as soon as you have occupancy, then ventilation needs to be the driving force. We have to flush that space. But it's tough to balance, but that's how I would approach it and looking at the time.
This next person's wondering how UVC lamps affect energy efficiency. How much energy would you say they typically consume, assuming running a typical 8 a.m. to 5 p.m. office?
A lot of the UVC now, you can get LED versions. So I don't think they're going to be much different than just a light on as far as their energy consumption. So if you can offset it with a couple lights off in corridors or some other unoccupied spaces, then that's going to be your energy offset. But it is just a light bulb. So it is not a tremendous amount of energy. If you put them at your main air handlers, then it is also going to be less. If you put them at every distribution terminal unit, then that is going to be more of a consumption, but it's like adding another light if it's at a classroom level. With UVC, you only have the two levers, time of exposure and intensity of the light. So based on, that's why we want to put them at the main air handlers, because your coils are generally the place where the air is moving the slowest, which means you need the fewest lights at that point.
Great. And while you're on that topic, what is the UV exposure time to kill the SARS virus?
It's about those two things. It's the intensity of time, and you don't get everything on the first pass. So we're looking at multiple passes, but if you can do it at the coils, that's going to be your slowest speed. And if you can get to under 200 to 300 feet per minute, that's going to be a really good kill time. Again, it doesn't kill it, it stops the replication. If you want extra protection, we are also we're doing about a 3 million square foot project right now where we're also putting it in the return air path. You can also add reflective mirrors just to have more of that bouncing of the light. And so you can do a lot of that to kill it. Now, anything with that can degrade, like plastics, seals, you want to try to keep out of that light. And then you have to have safeties to disengage the light, automatic cutoffs in case a technician opens that access door, but you want to kill the light because it is harmful to your eyes. Last thing, any functional performance test with UVC in the space, if you can see any blue light, then that's not good. So make sure it's always hidden from someone's eyesight.
Okay. Another related question. They're saying, Raj, we would probably consider the building-wide air change testing as an integrated system test as opposed to an equipment level FPT. Do you concur?
I do concur. It is what we struggle with right now is, do we run this based on what type of occupancy? Because right now, if you think about air systems, we're really driven by maintaining our thermal comfort, our temperature. So when do we override those based on our air change rate? So if your systems can handle that without losing control of the building, I agree that's an integrated test, but that's something you'll have to look at on a case-by-case basis. When do you switch to indoor air quality as your driver versus thermal comfort? So places we've talked about, they're like, if we feel like we need to lose a couple degrees of capacity to make sure we maintain air change rates, then that's where they would prefer to be.
Question on equipment. One person's asking, what are the risks to accepting responsibility for vetting these new technologies we're seeing in the field? Equipment manufacturers are typically very clear about the risk acceptance for the performance of their equipment. And how is this stuff being certified for this kind of service?
Good question. I'll do the first part, and then Serene, I think you can talk about risk for sensors and things. So the main risk that we see out there is the bipolar ionization. And I'm going to say, if you pick any of that equipment, use the UL 2998 standard. That will keep the ozone down. The risk from UVC, it has been used for decades, mainly to kill mold in coils. So that technology has been there. I like it in the air handlers because that's where we've seen it. It's been there for a while. It's tried and true. Finally, as far as ventilation and changing the filters, there's very little risk to bringing in more fresh air. From a legal liability standpoint, there's not a lot of downside. Of course, you need to make sure it's conditioned, you wring the moisture out. You don't want to introduce mold, but do no harm is your driving theme. But filtering the air, it's great. You're going to lose some capacity. So if you're worried about risk as your profile, start with running your units longer. Second, start to look at your filters. And then third, start bumping up the capacity of the ventilation coming in. And finally, fourth, the other technologies. Serene, you want to talk about the sensor risk?
Yeah, sensors are data collection, so there's not risk specifically from the sensors. But one of the things that the sensor data is used for is not necessarily just to say whether things are effective or not, but to also verify that the risks are not at a level where it's a problem. So if a manufacturer is saying that the ozone levels are low and acceptable, the sensors can verify things like that. And then for the sensors specifically, when I look at those, at Senseware, we have our sensors meet and exceed well and reset certifications, and those are the ones that we measure against.
All right. Okay. And Raj, when you have a second, do you mind pulling up that last slide that we had?
Oh,
again?
Yeah.
Thank you. So this,
no.
If you share your screen, this session is ended. Thanks so much. So I'm going to hop into the next question while you're getting that up. This question is about ASHRAE guidance. In the assumptions with regard to the viral load coming from the occupant load, does the ASHRAE guidance assume the masking of occupants? Reviewing these measures, there seems to be a tendency to view K-12 requiring ventilation and filtration requirements equal to what one typically sees in critical care hospitals.
Correct. So it is, again, going back to your risk assessment that you need to do with your client. If you want no possibility of transmission, then you have to treat it as a hospital. If we have a limited budget, like most of our schools do, then we have to look at time. So masks are there to make sure that initial sneeze, that initial distribution of the quanta is slowed down. So ASHRAE guidance does recommend mask wearing if there is a risk of that initial burst. You can sneeze and it can go up to like 26 feet. So how do you stop that initial burst is why the masks are deployed. Now, as you increase your time in a space, it eventually has to leave the mask. What that rate is, we don't have that all quantified, but it does become airborne, and that's where we say focus on your HVAC, your filtration, your air cleaners, and you ventilate that air and push it out. If you look at the Wells-Riley equation, it is also exposure time in that space where the ventilation systems can't catch up. So some of the schools I'm recommending, if they're going to full occupancy, then have all the kids in there for 2 hours and switch to another classroom or go outside. Let your HVAC run at least for 30 minutes without any generation of quanta, then they can come back in. So whatever that new protocol is, but I'm advocating for that versus just staying in your cohort for 8 hours and without movement outside or to another space, because the time will allow the buildup of the quanta, the buildup of the viral particles, and the HVAC can't keep up. So I hope I answered that question.
I'm going to stick on the ASHRAE topics. We have a couple more questions coming from there. Next one is, has there been any real life data testing done available in various building ventilation systems for the ASHRAE recommended indoor air quality improvement processes, such as higher ventilation, better filtration, air sanitization, shown on the infectivity or the transmittivity of the viruses shown in the charts that you had earlier in the presentation with actual COVID-19 viruses, or were they tested on other variants or other viruses available?
So most of the studies have been done on influenza, which is being correlated from a viral standpoint to COVID. Studies on COVID are now occurring, but I think it'll be a little bit late. There is a study from the University of Oregon with COVID, and that did determine that the COVID virus was found on the air handler filters. And so, again, on the return side of the filters coming back from the space, and it wasn't going in into the supply stream. So that is one study that has, and those are on HEPA filters. And that is one where we are using that as guidance on the filtration. But as far as looking at the studies of how, ASHRAE guidance on ASHRAE 170, which is the healthcare guidance on how we design healthcare systems, it is heavy ventilation, and those are predicated on air change rates as well as that HEPA filtration. So while we don't have COVID studies on schools now, we do have a rich history of healthcare design studies that we are now applying in this environment. So hopefully that kind of makes sense. When you have an airborne infection isolation suite in a hospital, how do we treat that after a patient's been in? We flush it out 12, 20 times, air change rates. How do you get an OR ready for the next patient? Some we do hydrogen peroxide, we fog it. Some we do 20 air change rates again. So that conceptual mindset has been based on decades worth of healthcare design that is now being applied to these non-healthcare spaces.
And one last ASHRAE question. Are you seeing PM sensors installed in the outside air intake to reduce outside air intake? If you have a high outside air PM reading, are you reducing the air below ASHRAE code?
So right now, we are not changing the ventilation rates as prescribed by ASHRAE 62.1. We are looking at EPA has weather stations, and if your PM levels go up higher, especially on the West Coast with fire season now, then that is a operational decision to shut those dampers down. and make sure that you're not causing poor indoor air quality. However, you can also pick it up with the filters and go with more frequent filter changes if your outdoor air is poor quality from a PM 2.5 level or PM 1.0. The only way to get the CO2 out of your space is through ventilation. So you have those two things that you're weighing. You have a dynamic system, so it doesn't have to be one size fits all. If it is from 1 p.m. to 3 p.m., which is peak fire or peak particulate distribution in the atmosphere, then you could shut it for a couple hours. And as soon as that CO2 starts to build up, then reopen it. And those are things that why the sensors are so important. So you can give your operators the ability to make different operational decisions based on the indoor air quality now, not the outdoor air quality, not the energy side, but what is the perfect air that you want to maintain inside, and then you can start to alter your systems in real time.
Great. That bleeds into our next question. Who is responsible for monitoring the dashboards and then communicating them with school facility staff, what the data indicates? And then in your opinion, how often is this done and how often should it be done?
So right now we monitor every minute. That became too much data. We were hired to monitor, analyze, and give direction as a recommissioning effort, in essence. So we can't have someone look at all of these sensors. It's data overload. So we are writing filters now to start to filter down the alarms. There's a lot of crossing the thresholds, which then turn into alarms. So you have to create that almost fault diagnostic detection for what do you want to see, and time is the biggest one. So whenever we cross these thresholds, and over 90 minutes, over 120 minutes, then those alerts come into us. Then we write the guidance of like, go to RTU 7, modulate the outside air damper to 100%, continue to run till sensor in that zone reads less. So it is going to be a mix of operating staff, engineers, and commissioning agents that need to start to monitor it, because when it goes way off, it's going to be this big troubleshooting exercise of why did that happen? Why did it go to the peak sensor value? And we can't have that if it's occupied.
Perfect. Okay. We have so many good questions, great engagement. I'm sorry if we don't get up to all of them, but I do want to sneak a few more in here. Let's pick a next one. Have you seen bipolar ionization being used often in schools? And if so, which HVAC systems are best suited for that? RTUs, single, multi-zone AHUs? What do you think?
I see the bipolar ionization being used mostly in terminal units, whether it's heat pumps, fan coils, VRFs, unitary ventilators, where you can't upgrade those filters. A lot of those, even window shakers, those filters, they're basically a bug screen. So if you can't get above a MERV 6, that is being deployed to help your filters become more effective. That's what the ionization is the best at. But you have to monitor for the ozone. And that's the balance. So as soon as you detect ozone, turn the bipolar ionization off.
Okay. I see Serene maybe typing this one, but I can read that one out loud. There was one sensor shown labeled for a coronavirus sensor. How does this sensor work?
So that's a pathogen sensor where you load the sensor with a biosensor. It's a disc cartridge that has half of it is the antibodies, the SARS-CoV-2 antibodies, and the other half is the luminescent protein of jellyfish. And the way it works is that it takes a sample of the air it tests it, the pathogens would bind to the cartridge. And if there is a positive hit and a match to that, and those antibodies, a light gets emitted with in the unit, in the sensor, and that basically tells you it's positive or negative hit. That particular sensor, unlike the other sensors, is not a continuous sensor. So you typically, the way we recommend it being used is that you look at the continuous sensors that are monitoring the conditions of the air. And if we're seeing a critical condition that is ripe for transmission, then you would initiate a test of the SARS-CoV-2 pathogen sensing specifically. And now we can have more conversations about that offline if needed.
Let me sneak this last question in. Can you measure viral loads?
Serene, you might have to.
With that sensor, yes. It's called a bioflash, and it's able to measure that. Yes.
Awesome. Okay, Raj and Serene, thank you so much for your time. Clearly, extremely valuable information. So many questions. We'll make sure to connect you with the presenters afterwards so they can follow up with any ones that were unanswered. We're going to be coming back again this Thursday to get into developing the best building envelope commissioning program. This same time, Thursday, please join us. And really, thank you again, Raj and Serene. Amazing presentation, and hope to see you again later this week. Thanks all.
Our
Thanks,
pleasure.
everyone.
Thank you, everyone.
Thank you.